sun. This floating ball of light has intrigued the human imagination since the dawn of time. This can be seen through various cultural and religious expressions of many ancient civilizations. From ancient Egypt to the Grand Roman Empire, deities associated with the celestial body were worshipped. For example, the ancient Egyptians used to venerate the god Ra, often represented as a man with a falcon head and a solar disk on top of his head. The primary center of his worship was the city of Heliopolis. The ancient Greeks also had their sun god, who was Apollo, the son of Zeus and Leto. Apollo was represented as a strong, beautiful, and radiant young man, evoking the idea that he was the sun itself. Even though the sun may not be considered a deity in the sense of ancient civilizations, it certainly deserves reverence. Being the primary provider of energy to our planet, we can affirm that it is thanks to this gift that life has prospered, as we know it today. According to scientific data, the sun produces approximately 3.8 times 10 to the power of 29 watts every second. Just to give you an idea, this amount of energy would be enough to power a city the size of Sao Paulo for the next 3 trillion years. But where does all this energy come from? How does the sun manage to produce it? For many years, the scientific community pondered this question. It was in the early 1920s that the British astrophysicist Arthur Eddington first theorized for the first time that stars generate their energy through a process known as nuclear fusion. Nuclear fusion is the process in which the nuclei of 2 or more atoms merge to form a heavier nucleus. The interesting aspect of this process is that the newly formed nucleus has a mass smaller than the sum of the nuclei that fused. This occurs because during the fusion process, some of the mass is converted into energy. In other words, the sun is a colossal nuclear reactor that is constantly transforming hydrogen atoms into helium atoms and releasing energy in this process. It's interesting to note that nuclear fusion, despite being a highly efficient way to generate energy, can only occur in very specific environments, such as the cores of stars with extremely high temperatures. Now let's take a closer look at how nuclear fusion occurs in the sun in a bit more detail. The first point to observe is that the sun's core, with temperatures reaching up to 15 million degrees Celsius and pressure approximately 340 billion times greater than Earth's atmospheric pressure, provides the ideal conditions for this phenomenon. These conditions are necessary because for elements to fuse, they must overcome the electrostatic repulsion force that exists between them. This force is known as the Coulomb barrier. Additionally, the sun possesses an abundant supply of hydrogen, accounting for approximately 97% of its mass. Hydrogen is the simplest and most abundant element in the universe. Its atom consists of a single electron orbiting a nucleus composed of a proton. Nuclear fusion can occur in various ways. However, according to astrophysical studies, the most common process occurring in the solar core is known as the proton-proton chain. The proton-proton chain can be subdivided into 3 main stages. In the first stage, 2 hydrogen nuclei merge, and one of the protons transforms into a neutron, releasing a positron and a neutrino in the process. The positron is a particle similar to the electron, but with a positive charge. Because of its positive charge, the positron immediately annihilates with an electron, and the mass of both particles is converted into energy. This stage is the slowest and takes about 7 billion years to complete. The resulting element of this process is known as deuterium. Deuterium is an isotope of hydrogen. Isotopes are variations of a chemical element that share the same number of protons but differ in the number of neutrons. In this case, for example, hydrogen contains 1 proton and 0 neutrons in its nucleus, while deuterium has 1 proton and 1 neutron. In the second stage, the deuterium nucleus formed in the previous stage merges with a new hydrogen nucleus, producing a helium isotope and energy in the form of gamma rays. This isotope has 2 protons and 1 neutron in its nucleus, making it lighter than helium. In the final stage, 2 helium isotope nuclei merge, producing helium, 2 hydrogen nuclei, and energy, thus completing the proton-proton chain. If we compare the mass of the final helium atom with the mass of the 2 initial hydrogen atoms, we will realize that 0.7% of the mass of the original protons was lost. This mass will have been converted into energy in the form of gamma rays and neutrinos throughout the entire chain. All the energy released in the form of gamma rays will interact with electrons and protons, heating the interior of the sun, keeping its core stable and preventing it from collapsing under its own weight. Now you may be wondering, if the fuel that keeps the sun functioning is hydrogen, what will happen when it runs out? Well, theoretically, when all the hydrogen is depleted, the sun will enter a new phase, and from then on, it will start fusing helium. This will cause it to expand to about 150 to 200 times its current size, becoming a red giant. Possibly, the planets closest to it, such as Mercury, Venus, and even Earth, will be engulfed. From then on, the sun will slowly and gradually expel its matter into space until only its core remains. The core of stars in this stage is called a white dwarf and no longer produces energy. Over thousands of years, this white dwarf will cool down until it finally fades away, and that will be the end of the sun. The good news is that according to estimates, it will still be about 5 billion years before the sun emits its last ray of light. Most likely, humanity will no longer be here to witness this event, perhaps having ceased to exist. Or maybe we will have conquered the stars.